All right, let's get going. It's a lot. I actually have a lot to cover today. Welcome back to day 2 of data structures. I am still Chris Gregg, and we are. Hopefully, you're still here for data structures. Thanks for coming out on this frigid morning. To anybody who didn't come out and watching this on video, well, I guess that's allowed. So, but thanks to those of you who are here. I'm sorry it was so cold out today. Today, we're going to talk about a few things. First things first, the anonymous feedback. I did get a couple pieces of anonymous feedback. One person I was able to reply to was a question about when the midterm is. The midterm is actually before spring break, for those of you who wanted to know that. And I was able to reply to that person. Another anonymous feedback I wasn't able to reply to because whoever did it didn't sign up for the email reply. And that's fine, too. But you do have to kind of sign up for that if you want an actual reply back. But suffice to say, I got the feedback, and I appreciate it. And feel free to use that as much as you want. A couple other things we're going to talk about today. We're going to talk about this thing called the We Code Conference. And actually, we have another representative from the computer science, the Women in Computer Science group, which I'm going to let Jesse talk in a minute. And then we're going to do a Unix tip of the day. I know a lot of you guys have not used Unix, the terminal window, very often in previous classes. And I kind of figured, hey, every day I'll just give a couple quick little Unix tips that will help speed things up when you're doing your own development using Unix. So just something quick on that. Then I mentioned the other day the obfuscated C contest. I'll talk a little bit about that just to show you something that I thought was kind of interesting with that. And then we'll talk about homework 1. I think technically homework 1 is actually due tonight. I thought it was going to be due last night, but I think the provide system is going to be open until tonight. So if you still want to do homework 1 and you haven't finished it up yet, fine. You can do that. And then we'll get into the meat of the lecture, which is this thing called dynamic arrays. And maybe a little bit, I don't know if we'll have time to talk about analysis, but we'll get there. So Jesse, you want to come up and give your little spiel?
Sure. Hey everyone, I'm Jesse. I am the former president of Women in Computer Science, also known as WIC. And we're having an event during Open Block on Monday to get some new members and just gather some interest and have some elections to look some new people in office. And it's just going to be a fun new event, very casual. So if anyone wants to drop by, more information will be sent out through the CS department. So we'd love to see you there. Any questions?
Jesse, do you want to talk about the We Code Conference? You know anything about it?
Sure. The We Code Conference is a great opportunity for women to get involved, and I believe it's a hackathon, right?
I'm not sure it's a hackathon. What it is, it's called the We Code Women Engineers Code, and it's for those of you females in the audience who want to go and attend this, you can sign up. I don't know if it's a hackathon, but I think it's got speakers, workshops. There's a little recruitment boot camp, which if you're looking for a summer job or some other job long term, you can certainly to go there. But I just wanted to throw this up there today so that you'd know, that the sign up is available, and I'll put it up again next week just to kind of remind people.
Yeah, it's a great opportunity. It's always fun to kind of go to these things. So.
Yeah. OK, thanks, Jesse. Any other questions on the intro items? OK, let's jump right into my Unix tip of the day. So most of you guys at this point have hopefully figured out that there's this Unix command called ls, which lists your directories, or it lists your files and the directories in the directory system in Linux. It has a number of different flags that you can call to get you a better listing, and I'll show you a couple of those. There's also this command called cat, which stands for concatenate, which means to put two things together. And normally it's used to print out a file. I'll show you that. And then there's this other command called less and another one called more. Actually, more came before less, but they do basically the same thing. They print out your file and in nice chunks that fit on the screen. OK, so let me see this. I'm going to try out this thing where I have a little window. If I type ls up here, let me see, actually. Maybe it's not going to work. It doesn't look like my window is quite big enough. Hang on. That's what happens the first time you try these things. OK. Let's go into Tufts. By the way, if you want to clear your screen, there's a nice clear. You can also type reset, which also works. Can everybody read that in the back? Maybe can you read that? OK, good. I made the font size big enough, and I'm using some funky font that I like. OK, if you do ls, all you get is this list of programs like this, right? Well, that that helps you see all the programs. But there's a couple of flags which are, I think, much easier. The A flag says list all your files. There's some files that happen to be hidden here. OK, any file that starts with a period is hidden to the Unix file system unless you use -a. And so it will list all of your files, including all the ones that start with period. And you actually have a bunch in your folder. There's a lot of preferences and things. There's also, and you can put multiple flags here, ls-al, I think is a very good one, because what it does is it lists all your files with extra information. OK? Over here, it lists something. If it starts with a D, it means it's a directory. And then it lists all these things called permissions. Bottom line about permissions is you probably won't have to worry about them for this class or for other classes. But what it is it allows you to have a bunch of access to the files. And then other people who happen to be in the group that you're in can have access. And it also allows anybody to have access if you want to set those up. Right now, this says, I, Chris Gregg, only have access to these files, which means I have read access, write access, and executable access, which means if it happens to be an executable. That's just something to keep in mind. Don't worry about this column. It's silly. The other column is you. There's a group that happens to be in. This is the file size. And then most important, I think, is when the file was actually created or modified last. And by the way, make uses that to tell whether or not you've modified a file since the last time make ran. OK? And then the file name. OK? You can also, I like the one that I've used probably the most these days is -alrt, which stands for all files in this nice list format. Reverse the order you're giving them to me in and sort by the time that they are. So if I do this, what it tells me is it gives me the last things that it shows me are the last files that I modified. So I kind of like that to use that. And it works pretty well. This happens to be my history file, which every command you run goes into a history. You may not be using the same shell as I'm using, but you probably have a history back there as well. So anyway, that's the ls command. The other command is, let me do this. Let me go into the homework server. The other command is these two commands called, well, the command called cat. Hang on, let's see. We're going to go to day 2. Let's go into heights, which we'll talk about later. And there we go. If I want to see this file, heights.h, OK, and I just type cat and then heights.h, OK, what it does is it prints out the whole file for you onto the terminal. OK, so if you want a quick snapshot of what your file looks like, cat and then the name. It's not too useful because it does the whole thing at once. So there's two other commands, more and less. I tend to use less these days because it's actually better than more. But if you do the same thing, type less and then heights.h. Whoops, my window's not quite set up correctly. Heights.h, then you will get a nice little window that only prints the first part of the file. And then you can use the arrow keys or the space bar to go down. Space bar gives you a whole other page. Arrow keys to go up, and you can go down and up like this. So it's a nice way to go through the files. We'll do a bunch of this today when I show you what this file actually is. OK? So that's our, whoops, and then you hit Q to get out of it. And it actually gives you back the window that you started with. OK? All right, so that's our little Unix tip of the day. We'll see more of that. Use those commands as much as you want. Any questions on those? All right, great. OK, so next. Obfuscated C. I mentioned this. I just thought I'd show you what's going on here. Can you guys see? You may not be able to read this from all the way in the back, but that is actually a program. OK, it's written in C, and it's actually a program. And the author of the program actually made it look like the word fluid, F-L-U-I-D, right? And you can actually tell if you go up here. Let's see if I can zoom. Oops, cannot zoom in there, but oh, there we go. Well, zooming's not working so well. You can kind of see it says. You can see where it says include studio.h, blah, blah, blah. So it's actually C. But notice it looks like garbage, right? Well, this is part of this contest. OK? You can actually compile these for your own computer and then run them. Somebody was nice enough to actually put this one let me see if I can do this. This one, can I open it? Hyperlink. Can I open it maybe? Hang on. Open hyperlink. There we go. All right. Somebody's been nice enough to put this one online, and they put music to it. So hold on. Let me get this. OK. So what's going to happen here? Let's see. Oh, it's bigger than I thought. Hang on. This. What's going to happen here is somebody's going to actually run this as if they were in a terminal window and do this. And by the way, you win prizes for being most clever. OK, so this program is going to be run, and let's see what it looks like here. I could probably do this. Nope, let's do this. Let's not do that. Leave it at there. OK, so they're just compiling it right now. Just compiling it, and then they're actually, what they're doing is using another fancy Unix command that pipes in the program into the file. And I kind of, there we go. And now watch what it does. That little tiny little program fits in one window and does this. All right? And then he didn't stop there, by the way. The guy who wrote this, he also has other files that, like, so this is another file just called column. It's just a bunch of columns. And then he pipes it into and he runs it with his program. And by the way, these are like text. This is not graphics, right? This is like, you can see like semicolons and slashes and things in here, right? I mean, that's how amazing this is. The guy seems to know something about physics and was able to do this. So pretty cool stuff. I'll show you a couple more here. This one's kind of a neat one. And you can build your own. Like, you can like design your own thing and then see what it does. Because it's just an engine that runs these things, right? Huh. I mean, it's one of those things where you make something simple enough and follows these rules. It's kind of physics, right? You can do this. Let's see. I think there's one more that was kind of clever. And then there's one at the end I do want to show you as well. Oh, well, this one's cool. More or less the same thing. Right? Water just flowing down there. OK, and then let's see. Here we go. OK, so then he has one like little sneaky one that does color as well, which is kind of cool. And the program's like 5 lines longer. And it does this. So anyway, wanted to show you that. Please do not make your code obfuscated. We will not be able to grade it that way if you do that. Bruce actually showed me another one. Let me see if I can back here. Bruce showed me another one that was kind of fun. Where'd it go? There it is. So see this little program here? This little program up here, this little thing. See how it looks like? It kind of looks like a flag. Well, this is actually kind of cool. Being in the Navy, there's all these flag symbols that you can use. They call them semaphore flags. Okay, and what happens is if you're on a ship and you're on another ship and you have binoculars, well, if you want to communicate between ships and you don't have a radio, not that you wouldn't, but if you don't have a radio, you don't want to talk on the radio, which is a big deal. You use these semaphore flags. So if you want to do the letter A, you have these 2 flags and you're like A, right? And if you want to do B, you go B, and whatever. And then you can pass messages back and forth just by sight. Well, some guy wrote this little program, and then let's see, where is it here? Whoops. There we go. If I go to obfuscated C, I actually ran this on my computer. And if we do, let's say, echo data, data structures, and then we do the same thing where we actually make the program run it. Whoops. Anderson, there we go. What it does is well, can't really, here we go. You can see this little guy. This is like a little guy. And he's like holding up the flags. And then this is the next little guy here, holding up the flags. And then for the space, you just have the flags down like this. Anyway, this is what that one does. And it's just, you could see it looked just like nothing. So the best part about this one was this won the contest under the category best use of flags. So I think that was the best part about it. But anyway, all right. So as I said, please don't make your programs look like that. All right. Now, let's go into talk about homework 1. As I said, it's actually technically due tonight, so you still have some time to do this. But Bruce and I decided to throw in a couple little things into the homework one, just to see what you guys would do with it. Okay, the two things that, and I think if you went on Piazza, you'll notice these are the things that the most questions got asked about. In the first part of the header file, you'll notice there's this thing called, it says assert that, well, actually, we'll get to the epsilon in a minute. In the header file, it says assert that the width and the height are greater than 0, right? And then that was really all we said about that. And then a bunch of people asked questions about that. Well, if you're modeling something real, like rectangles, right, you can't have negative lengths or negative widths for rectangles, technically. Okay, I mean, the math works out if you just type it in and have that. But we said, hey, look, let's make sure that your program actually doesn't accept negative values or values that are 0 for lengths. And what you can do is you can actually do this error correcting or this what's the word I'm looking for? You can actually check for these sorts of things yourself if you want, or you can make the compiler do it for you. Okay, there's this fun command called, or this fun library called assert, which gives you the following ability. In your program, you can write assert and then whatever you're trying to assert is true. In other words, whatever you're trying to say, hey, is this true or not? You put that in parentheses, and then that's the end of your command. And then the compiler, well, the runtime, when it gets here, it says, is the width greater than 0? And if it is, it just goes on to the next line in the program. If it doesn't, if this isn't true, it actually crashes your program, or I should say exits your program, with a nice error message for you. Okay? Now, some people ask, where do we put these assertions? Well, you put them in your, well, in this case, you put them in a couple different places, but in particular, you can put them in your constructor. Now, why would we put them in the constructor? Why wouldn't we just say, in our constructor, do some error checking? Like, for instance, in the constructor for the thing, say, print out a message that says, your value is less than 0. Please enter another value. Are you going to want to put that in your constructor when you create that? Any ideas? The answer is no, you wouldn't. And the reason you don't want to put that in your constructor is you want that to work. You don't want to have input-output inside like your actual constructors. You want to kind of separate the input-output part from the actual program that you're trying to run. It simplifies things, and it makes it easier to change things a little later. So we'll get that. But anyway, let me show you what happens when you do an assert. Here we go. Assert example. I have an assert example here that is, let me show you what it is. We'll use less, although it's not that big. Assert example.cpp. Here's all, this whole file is like right here. Right? All this does, this says, we're doing a file, we say, we have an integer, it's 0, another integer, b, which is 10, and then we just write assert a is less than b. So a indeed is less than b, so the program will get here, and it'll say, no problem, let's go on to the next one. And then it says assert b is less than a, and we get to here, and then it says, no, it's not right. Okay, that doesn't work. All right, so here's what happens when we do that. Okay, and here's what it did. It says assert example CPP line 9, the function assertion b is less than a failed. That's a pretty good error message for the program runtime to do. The compiler actually figures out where in your program this assertion happens, and it encodes it into the program itself and gives you this nice error message. Somebody on Piazza said, well, is it all right if I just print out error whenever I have one of these errors? You can do that, but that doesn't tell you much about it, right? That's not a very good error message. And if you're doing programming, you do want error messages to be relatively straightforward and tell you something, right? Error doesn't tell me anything. This tells me something. It says on line 9, my assertion failed. Okay, so that's why we do those. Okay, questions on assertions? There were some here. Yeah.
I think the example, when you think of for assertions, is used a different library, like assertions.h.
We may have used assertions.h. It's the same library. It's just You can use either. It should be the same library anyway. Yeah, good question. Anything else on that? There will be no points taken off if you didn't do this on your program. So don't worry about that. I'm just kind of showing it. This is kind of a little extra in the program to show you that. OK, so that was assertions. Then we also had this epsilon was thrown in there. OK, and epsilon's interesting. So raise your hand if you've heard before this assignment you should not compare floating point values to each other. Probably like 10% of you raised your hand. OK, here's the bottom line for this. OK, when you are, well, let me just describe it like this. If you have a rectangle, right, and the rectangle is like if it's 3 and 3, OK, and those are actually integers. OK, they're not floating point values. The computer can take an integer and it can put it in memory somewhere. OK, it can put it in memory, and it can say, OK, this part of memory, this has the number 3, and it represents it somehow. This is going to get a little bit into computer architecture. But it represents that number explicitly. OK, most computers with integer values can actually represent 2 to the 32 different values. OK, 2 to the 32 different values, which is about 4 billion values. OK, and you can do that. And integers, the nice thing is, how many integers are there from 0 to 4 billion? 4 billion, right? Or from negative 2 billion to 2 billion, if you want to, the range is there. But there's 4 billion there, right? And we know that because they're integers. OK, fair enough. Now, if, however, and if you're comparing integers, and the computer says, look, do these two integers compare to each other correctly? Well, it can say this is a 3 and this is a 3. And I know there's only, there's 4 billion different combinations, but are they the same of those 4 billion? Yes. OK. Now, let's say that we had 0.3 and 0.3. In other words, they're now floating point values. OK. The computer is still going to take 2 to the 32, or be able to represent 2 to the 32 different values that are floating point values. OK? How many floating point values are there from 2 to the 32? In other words, how many decimal numbers are there from 0 all the way up to 4 billion? An infinite number, right? So there's an infinite number of combinations you can do. Okay? As it turns out, the way they built this in, you can actually represent numbers from about, in regular floating point, from about 10 to the negative, I just looked this up and I forgot it already. I think it's like 10 to the negative 30 or something like that, all the way up to 10 to the 30 different numbers in this representation. Okay? That is a whole lot of different numbers. Okay? You can represent that many. In fact, if you go to doubles, or I guess the next level up, you can get like 10 to the 300, all the way down to 10 to the negative 300, which is a huge range. Right? Does anybody know how many, roughly, not that you've counted, how many particles there are in the known universe? Like atoms, electrons, atoms? You got 10 to the what? How many different particles do you think there are? 10 to the something. What is it? 90 or 120? OK, any other guesses? 10 to the 26th? Any guesses like, sorry? 45. 45, yeah. It's about 10 to the 82 the last I looked. Right? So you're in the right, well, range is, we've got to be careful there. But this is a huge, huge number. But we can actually represent numbers even bigger than that, than the number of particles in the universe, in this space that we have here. OK, where's all this going? Well, all this is going to the fact that when you have a floating point number, you only get so many different representations available to you. OK? And as it turns out, the way you end up at a number determines whether or not that number is going to be the representation you think it is. Or for that matter, what mathematically you think it is. OK, let me show you what I mean. Let me just show you what I mean. If we go back to, our window here, clear, and we run a program called Python, which is another programming language. And the reason I'm using that is because it's much easier to actually do quick little demonstrations. Don't worry about the syntax. But watch this. If I say a equals 0.1, okay, we all know what that means, right? A is 1/10. All right. B is 0.2. And C is going to be 0.3. Okay? If we have those numbers, right, 0.1, 0.2, and 0.3 in our variables, and I write a statement like this. This is actually very similar to C. Okay? Well, in this case, it's exactly similar. Okay? A plus B equals C. Okay? So our mathematical brains know that 0.1 plus 0.2 is indeed 0.3, correct? That's that's relatively obvious, right? But if I do this here, we get false. Okay? And these are numbers that are not, particularly hard to understand, right? They're like really simple, easy numbers, right? But the computer thinks they are not the same. If I actually show you what the computer thinks A is, there's that on there. I typed in A equals 0.1, and the computer says, no, it's actually 0.1, right? Well, and the similar sort of thing for B, right? And then C, it's not 0.3, it's 0.2999999, right? Why is that the case? It's because the computer only has a certain number of values that it can store. And when it stores your value, it gets it again, and then it may not be exactly what you think it is. But it's really kind of close enough, right? Close enough for government work, as they say, right? So, but it's not exactly the same as you might think. Okay, the reasons are that there's only the certain number of values it can store, and the computer stores values in binary representation instead of decimal representation. So numbers like 0.2 and 0.3 and 0.1 don't come out correct exactly what you think they are in binary representation. So that's the reason we can't actually do these comparisons. Okay, so in your program, okay, well, you can't actually, you're not allowed to say, like some people tried to do, what am I talking about? If width equals height, then do something, right? You're not allowed to say that because you're using floating point values, and that problem we just showed comes up and bites you, okay, when you try that. Instead, what we've decided to do is we just put in this constant called epsilon, okay, and I defined it. You can either define it or use it as a constant. Defined epsilon to be 0.00001, or maybe one other decimal here and there. How do you compare two numbers besides looking at their equality? Like, how would a computer actually compare two numbers? Any idea? Yes?
Take the absolute value of the difference, see if it's less than epsilon.
Take the absolute value of the difference and see if it's less than epsilon. Perfect. Okay, so what we're going to do instead is we're going to say something like we're going to say, you could say if width minus height, right, width minus height is less than this epsilon, right, do your thing. But you do need an absolute value, because what if the width happens to be 3 and height happens to be 10? Well, then you'll always be less than epsilon. So you do have to take the absolute value. Well, you guys in other classes might have used a math library. There's a math library if you do include cmath, like that. And then you use a function instead of just this. Let's do it this way. FABS for floating point absolute value. If the floating point absolute value of width minus height is less than epsilon, then you say that it's a square. Why? Because the subtraction of two values meets our little requirement of being less than this value. Okay? And it all goes back to how computers actually represent numbers that are not integers. Okay? Again, we won't take any points off if you didn't get that one correct. Okay, questions on that? Any other questions? Yes?
Is the absolute math library different, or absolute value of math library different than the absolute value of the standard library, the standard ABS?
I don't think so. It should be the same. Yeah. In fact, you could write an absolute value function very easily, and it's almost certainly identical. Yeah. Other questions? Yes?
So
there a built-in like equals to handle floating points?
Isn't there a built-in what to handle floating points?
It's equal. Like,
Oh, it's equal. There may be. I'm not sure. I haven't used that before. I'll have to look it up. I'm not sure if that exists in the library. There may be. Yes.
Is there a benefit to defining epsilon instead of like making it a total function?
Yeah, good question. Somebody else asked that on the internet system. If you define it as this, the only difference really is that, well, there's two differences. If you actually use the define preprocessor, right, number define, versus setting it as an actual constant, this says anywhere in your program that it finds epsilon, replace it with this number. And that's fine. And it doesn't take any other space. And it does that before any compiling ever happens. So that's fine. If you define it as a constant, you do use a tiny little bit of memory, because that constant does sit somewhere else besides right in your program. But you can also, the nice thing about defining a constant is you can limit it to certain parts of your program only. So it's what we call respects scope, the scope of your variable. I don't care which one you do. You'll see either in things. Okay. Any other questions on using the epsilon? OK. All right. So that was basically all I wanted to talk about the homework. We will try to have the homework graded for you after, by, let's say, Monday at the latest, I'd say. It's pretty easy to grade this one, so it should be even quicker than that. But I had a big meeting with the TAs last night and told them that we're going to try to grade as quickly as we can. So hopefully that'll do it. All right. Good. Let's move on to something that's actually data structure specific. Okay, we're going to talk about this thing called dynamic arrays today. All right. Now, you should have seen arrays before, and possibly dynamic arrays. I didn't get a chance to ask if you guys saw dynamic arrays in Comp 11. Did you see dynamic arrays? OK, so you'll get most of what I'm talking about here. OK, we're actually going to start with regular old arrays. OK, and I put a couple of files on the website and under the lectures. This file called heights.zip and heightsdynamic.zip. What we're going to do this morning is we're going to build a little class. Well, I've actually built it, but I'm going to show you the class that I built that allows us to get averages of celebrity heights. Okay? Turns out that if you go to the internet and you type in celebrity heights, there's like celebrityheights.com, and it lists all these like 6,000 different celebrity heights. And so I wanted to find the average of that, because I think that's a really important statistic when you live in a first world nation, what your celebrity heights are, right? And so we're using up internet bandwidth to do this. But what I'm going to do is we're going to create this little thing. We're just going to figure out a little class to determine what the average heights are of these celebrities. OK? So I think that's all we're going to do with the PowerPoint for now. There we go. All right. Let's get out of Python. Go into heights. Here we go. All right. So I've written a couple of files, as you can imagine, a .h file, CPP, and a little tester file, kind of like your homework. OK? And let's look at what the H file says. This is the best way to understand a class, by the way, if you look at the .h file before you do anything else. OK. All right. And by the way, I'm going to talk about a couple C++ specific things today, which you'll kind of have to know, although you don't have to use them. And but they will make your life a little bit easier in some cases. OK. So in this file, we have this thing called a typedef. Did you talk about typedefs in Comp 11? No. OK. Here's what a typedef is. OK. A typedef says the following. OK. It actually says exactly what it sounds like it says. It's defining a type, a new type, like instead of saying an integer or a float, you're going to define this new type. Typedef. OK. And then you can put in, say, int. OK? And then you can put anything after that. Let's say Boris. Right? OK. Typedef int Boris. What that says is, in your program, anytime you see a type that is Boris, it's actually an integer. That's all a typedef is. Okay, so if you write you write this, you write typedef int Boris, and then later in your program you write Boris A, right? You go Boris A equals 3, right? Well, the compiler will say, oh, I know what Boris is. Boris is an integer. So that's going to be now an integer type. Okay? And the question is, why would you even bother doing this? Well, here's why. And this is the powerful part of this. I left this blank right here. Okay? In this program, I happen to have celebrity heights in inches, right? If I had celebrity heights in feet with decimal places after them, right? Actually, some of them do have decimals, but that's irrelevant right now. If I had this in feet and wanted to use a floating point value, all I would have to do is wherever I have this typedef later in the file, and right now I'll put int, but later I might say, oh, I want to make those float values, right? I just change the int here to float, and then the whole rest of my program, every time it sees that value type, it knows that it's a floating point value instead of an integer. So it makes it real easy to change your code based on the type of some large variable that you're going to use a lot. Okay? And that's that. Now, I'm not using Boris in this. I'm actually using a boring old name called value type, which just defines what kinds of values we're using now. Okay? And in this case, it's going to be integers for those heights. OK. Don't worry about the rest of this stuff here. We'll get to that at a later time. OK. Let's see. Let's go down here. OK, here's one of our constants we were talking about before. Static const. Here's what this means. This means don't touch this variable. Right? You're not allowed to change it. Basically, that's what this capacity variable means. Here's another typedef. Okay? This typedef is called size underscore t. And if you read a lot of C++ code, you will see this everywhere. So I figured I might as well introduce it now, even though you don't have to use it. But what this means is this says this is it's a variable type that allows you to reference something in memory, and it will be big enough to hold that amount. Okay, so for instance, we're going to be talking about arrays, right? Some arrays here. If you have an array and your computer is allowed to create some array of a certain length, okay? If you refer to, say, element 3, 0, 1, 2, 3, this element 3, right? The type that we use to talk about the number of the element is going to be big enough to represent all the elements. Okay, it's the bottom line there. It's not that hard. You'll just see this a lot, so I figured I might as well use it in here. Basically, it's an integer, and basically you'll use it when you do something like if this was our array called data, and you wanted the element 3, you would do data 3. Well, that 3 is going to be a type that allows you to represent all those numbers. That's all that is right there. OK, questions on that? Typedefs? They're pretty straightforward. They're kind of boilerplate stuff that you'll see a lot. OK, all right. We have a heights constructor. That's all I'm going to put for this one. Just a little constructor that creates this array that we're going to do. And then I have a couple of functions in here. We're only going to use the append one, as it turns out, for this one. Append says, OK, I'm going to have this value type. And by the way, this little ampersand here means that it's a reference variable. What that means is you can refer to, it will actually change the original variable. Okay? There's kind of a long story about how variables get passed to functions that we don't really need to worry about right now. But suffice to say, this will allow you to change the actual value itself later. And this is not strictly necessary for this example, but I thought I'd put it in there to show you. What this does is it adds a value to the end of the list. So we're going to have this array here. Okay? And let's say the array has 3, 1, 2, 4 in there. Okay? Append will say, give me a value. And it will take that value, and it will just stick it at the end. Let's say it's 5. It'll stick it right at the end. Good enough, right? Insert is kind of the exact opposite. It adds a value at the beginning of the list. Okay? And here's how I've actually written it. Again, we won't even use it today. We'll get to it a little bit later, maybe. But what I've done is I've said, and I haven't been very clever about it necessarily, but I've said, OK, we're going to insert the number at the beginning of the list, go to the end of the list, move this one here, 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 and then insert the new one right there. OK? Not particularly clever for an unsorted list, right? The more clever solution would have been take this one out, move it back here, and then put it there. But if it's unsorted, who cares which order they're in anyway? So it doesn't really matter. But I threw that in just to have it there. OK. Then we've got an erase, which actually erases the value there. We're not even going to use that this morning, but it's there for later if we use it. OK. And then a couple other functions. The size function, or method, returns a value that's a size t. It's that integer we're talking about that tells you how many values are in your array. So in this case, if I do size, it will give me 1, 2, 3, 4, 5. It'll say 5. OK? It won't say 4, which you might think it would say, because this happens to be value 4 out of 0. But it tells you how many are actually in there. Yes?
In this case, is your actual array much larger?
We'll talk about that. Yeah, good question. The question is your array larger than the number of values we have in there? Not sure yet. OK, we'll get there. Good question, though. OK, and then we have value at. OK, the value at says, give me the value at, say, location 4. Pretty straightforward. OK, it takes this size t as the index number, and it gives you back your value itself, OK, in a value type. OK, and it says, hey, look, if you're going to ask for some index, well, the size better be bigger. The size of the array better be bigger than the index you're asking for. Otherwise, you should fail. OK? All right. And then finally, I have in here the average height. OK? And the average height is the function I'm going to show you that actually takes the numbers and does the height. OK. Questions on the header file? OK. Nope. All right. Good. Let's look at the CPP file to see how I actually did this. OK, a bunch of boilerplate stuff. And then let's see. OK, I've redefined the capacity here. OK, I've redefined the capacity. Did I say what the capacity was in the other file? I think I did. I think I put the capacity as 5 right now, just for kicks. I made it 5. OK, here's our constructor. It is a very simple constructor. All it says is used equals 0. OK, in other words, how many do we have and how many elements do we have when we start out? 0. Done. That's it. OK. Here is my append function. OK. The append function, which we said what it does, it says, look, is the size less than capacity? Yes. And then it says our data, which is our array that we've created. It says of the used, which by the way, size returns used because we're in the heights file, we are in the heights class. We actually can just refer directly to used because it's a private variable and we are part of that class. Data used, in other words, if there's 0 elements in there, make the 0th element equal to our value, and then increment the number we've added. OK, so every time we append, whoa, I do not want to do that. Thank you. Every time we append, OK, we have the number. Well, I should have left it on there. 0, 1, 2, 3, 4. OK. So in this case, the number of elements, 1, 2, 3, 4, 5. There's 5 elements, meaning our used variable holds the number 5. OK, 1, 2, 3, 4, 5. And then it says if I'm going to append another value, OK, let's say I put 7 in there. Well, what it's going to say is make the value at the size amount that value. So it's going to say, OK, well, size is 5. So I'm going to make this one our number. And then I'm going to increment our size. So size goes from 5 to 6, because now there's 1, 2, 3, 4, 5, 6. Straightforward? OK. All right. Now, insert. I'm not going to worry about insert, but you do have to do this little loop to do inserts there. I'm not going to worry about that. And size is so simple. It just returns the used variable. That's for if people who don't own your class or aren't in your class use your class. OK. And then the value at is what we talked about. It just returns the value at that index. OK. And then finally, the average height here. This is a little function I wrote. It makes sure that the size is greater than 0. It's impossible to find an average of 0 values, because you end up dividing by 0, and that's bad, right? So you have to make sure it's 0, and then, or greater than 0. And then it says, OK, fine. We're going to have a sum. We're going to do a little quick loop that adds up all the values. And then we're going to divide that sum by the size of the array. And we're done. OK. Any questions on that program so far? I'm going to show you what it looks like when we actually run it. Any questions? Good. All right. So let's see. Let me make it. And then let me clear the screen. And then heights, tester. OK, enter celebrity heights. All right. Let's do this. Let's go. I actually have, I'll show you another Unix trick real quick. Data structures, day 2. Let's see, heights. OK. I have this celebrity heights list that I scraped off the internet. OK, and it's got all these different numbers. OK, so somebody give me a celebrity. We'll look for him. Anybody? Johnny Depp. OK, so let's do this. We're going to use this program called grep, which searches through a program. OK, I'm going to do grep Depp. It's D-E-P-P, right? OK, let's see if Johnny's in here. Hang on. Before I do this, hang on. My window thing is messed up. Whoops. Hold on a sec. Window, refresh. That should do it. OK, grep, and then Depp, and then our celebrity heights.txt. Johnny Depp. Here we go. Johnny Depp. Oh, you can't see all the way down there, can you? What? Why did that happen? I don't know why that happened down there. Hang on. Oh, because it's the wrong window. Hang on. Ah. I'll get it. Oh, not quite, not quite. There we go. All right, Johnny Depp happens to be 5'9", or 69 inches. OK? Johnny Depp 69, so we're going to put that in there, 69. OK, give me another celebrity. Jay-Z. Is it J-A-Y? J-A-Y. Let's see what happens here. And then celebrity heights.txt. Jay-Z is 73.5 inches tall. So we're going to just put 74 in there. OK? This is a pretty impressive list, right? OK, 74, and then one more. Kevin Spacey. OK. I think he's kind of short, actually. Grep, Spacey, oops. Spacey, and our celebrity heights.txt. Oh, there he is. OK, 70 inches. So actually, he's pretty tall. Well, 70, what is that? 6 feet? Yeah, he's taller than me. OK.
5'9".
Oh, 5'9", duh. 5'9". Ha, he's shorter than me. Ha. He's a better actor. OK, so sorry, what did it say? It was 70, right? 70, OK. 70, OK, so that's that. And then I put in here so that it does a blank line will do it. And it says, OK, look, number of celebrities is 3, the average height, 71. And hopefully, when you average those numbers together, you get 71. OK, pretty straightforward, right? If we run it again, and let's say I just make up celebrity lists, 71, 72, 60, 48, and then 75, right? If I do that, I think, yeah. Oh boy. All right, it says our assertion failed here, and it says our capacity, size is not less than capacity. We actually reached the end of our 5 celebrity list there our data structure that I gave it. OK, what's the solution to this? Bigger array. Sure, I could go back into the file, the CPP or the header file, and instead of capacity being equal to 5, I could say the capacity is now equal to 5,000, right? And then I can recompile, and then we can rerun and do that. Now, I have a question for you. How often do you get some error in Microsoft Word and it crashes, and you have to go and you have to get the Microsoft Word source code, and you have to go in and find and then change a variable in there, and then recompile Microsoft Word, and then start your program up again? Right? Yeah, all the time. It happens all the time, right? It doesn't happen, OK? Because that's not a great solution. It is a solution. I could do this. I could say, I'm never going to have more than 10,000 celebrities in my list, right? But then, like 10 years from now, all the celebrities, right? Now we have all their, and all of a sudden it's 10,001, and my program breaks, right? Well, let's try to make something even better than that, OK? And this is where dynamic arrays come into play, OK? I will do the same thing as before, let's see, heights dynamic.h, and we'll see what we've changed here, OK? A dynamic array, before I even go into this, a dynamic array, OK, says the following. It says, hey, I don't necessarily need to know how many items I'm going to have at the beginning, OK? It says, we're gonna say, OK, we'll start out with some array, and then we're going to add to that array by making a bigger array. Okay, it's kind of like let's say you had a train and you start out with one car in the train, and then you get to some stop and a whole bunch of other people get on, and you say, let's add another car to the stop or to the train. Okay? And guess what? It takes a little time to do that, right? So we're going to be able to do that though. Okay? We're going to say, here's our array that we start out with, and let's say we fill it up with celebrity heights, right? 72, 68, whatever. Okay, and we get to the end and we say, oh, we need a bigger array. Well, we can ask the operating system for more memory. Okay, and let's say we're going to make it one bigger, right? Well, what we're going to do is we're going to say, hey, give me more memory. Unfortunately, the operating system can't just say, oh, you want more memory? Here's another little piece right here. Can't do that. Okay, why can't it do that? Well, it has to do with the way it allocates memory. And you can't guarantee that this spot's not going to be taken up by some other part of your program or some other area. So, but what it does is it says, okay, you want more memory. I'll give you more memory. Here it is. And it gives you this memory here. Right? Now it's 4 long instead of 3 long. And now you say, all right, well, now I've got this new piece of memory, and it's big enough to hold my other value. It's got one more train car on it. But the analogy is a little bit broken in that it's not just that you're getting a new train car. You're getting a whole new train with one more car than you started with. So everybody has to get off this train and then get onto the new one, right? So you have to go and you have to move these guys on here. Now you've got a bigger array, and you can now put your other value in there, right? So that's what dynamic arrays are doing. They're allowing us to go and get more memory to make our structure bigger, and from that we can now not be limited by the number of the number of items we're going to put in this array. Okay? All right, let's see. Has anything changed here? Nope. See, is anything else? Here's something that's changed. In the .h file, I'm now saying the default capacity. All right? The default capacity is maybe the one I used before, 5. Okay, it doesn't matter. You can actually make it whatever you want. But smaller is probably better in the case that you don't want to waste memory. Okay? Okay, because you don't know if you're only going to put 3 celebrity names in or not. All right. So then we have the constructor. You can actually set the default. I'm going to let you set the default capacity. So you can either put it in there in the constructor, or it will get a default. Like it will use the default that we've set. OK, nothing has changed about append or insert or erase. All those are the same. This is a new one. Reserve. Reserve is the conductor of the train. When he gets to the station that needs a new train, he says, hey, give me another train. Right? That's what reserve is. It says, I need a new train that's longer. Right? I need a new array that's longer, and that's what it's going to do. And all that you ask for is a new capacity, a new amount of data. Okay? And size is going to be the same. Valueat's going to be the same. So not too much has really changed here. And average height, same. Okay? So we haven't actually changed too much. But we have to rewrite some of our code. Okay? Let's see how we did that. All right. So boilerplate. Default capacity is 5. We have our new constructor here. OK. I'm going to show you another constructor that you will not have to know right now. I'm going to gloss right over it. It's going to be for later. Okay? But there's this thing called a copy constructor. And all you need to know about that is at some point, if you want to say, here's a list, and I want a new list or something, and I want to make it equal to that other list, somehow the data has to get from the other list into your list, and it has to be copied. The computer won't do that automatically for you. It will with integers, right? If this is an integer and that's an integer, and you say a equals b, well, a is now whatever b was, well, is, right? You can't do that with your own classes directly. Okay? Why? Because you've got these data structures that you've got this extra data that you asked for memory-wise, and the compiler doesn't necessarily know exactly about that. It can't do it automatically. Okay, so let's see. Don't worry about the copy constructor right now. This is something we need to deal with. Whenever you ask for more memory, the operating system gives you more memory. And then it's like, that's your memory for the duration of your program. Well, what if you need a new car, and you want to add you need a whole new train, right? What happens to this old memory? Well, you have to destroy it somehow, because you don't want to waste memory. You want to give what you're not using anymore back to the operating system. That's what the destructor is going to do. Well, the destructor will do that when you delete your whole class, as it turns out. Okay? You have to have destructors in here. It's whenever you're using dynamic memory, you're going to have a destructor rather. The destructor just says, in it, it says delete the data that we came up with. And this little bracket notation says, oh, it's an array. Okay? Details are not as important right now. Concepts are more important. OK. And now, here's where we get to the real meat of what's changed. Before, we had an assertion that said if our size was equal to our capacity, or if the used, or size, was equal to the capacity, OK, we'd crash. Because you can't deal with that in a non-dynamic program. OK? Now what we do is we say, oh, we can deal with that. If we're at our capacity, reserve one more train car. In other words, give me more memory that's one more than what I started with. OK? And then it reserves that. We'll get to what the reserve actually does in a minute. And now it's got one more, it's going to have one more place to put your data. And guess what? You can put it there. OK? And then you increase used as well. And guess what? Now uses again at capacity once you've added. But who cares? We'll do it again, and we'll get there. Insert, same thing. We have to do the reserve business. And then let's see, what else do we have here? This is still insert. Sorry, the formatting looks funny on this big screen. OK. Do not worry about this either. This is the overloaded operator. We'll talk about that later. This is all stuff you don't need to worry about. And then here's reserve. OK. Reserve says, I need some new capacity. It's going to use that size, which says, give me a number that makes sense for this array to index it. OK. And it says, look, if you're asking for the same amount of capacity that you already have, just return. Don't change anything. Nothing needs to be changed. Why would you do that? Who knows? But you might write something that does that. Just return. If you are asking for a capacity that's actually less than the amount you've used, let's say people get off the train and you say, I don't need the train that big anymore. Well, what it's going to do is it's going to say, just let them get off and leave everything in place. Just say that we have less people. Right? That's all it's going to ask. OK? That's all it's going to do. It's not going to actually get a smaller array. It's just not going to bother with that. You could build that in there. If you wanted to, you could build it in there. I have not done that. OK. If those two cases aren't true, you're actually asking for more memory. OK. What it's going to do is it's going to say, it's going to use this keyword new. And it's going to say, give me another array of my value types, which in this case are integers. And it's going to say the new capacity. That's where it's going to give you this new, bigger array. OK? And then it's going to say, all right, copy all the data. We could write a little loop to do this copy. Instead of doing that, I used a library function that says, give me the beginning of the data you want to copy, give me the end of the data you want to copy, tell me where you want to copy it to, and go. And it writes the little loop. OK, it writes the loop. All right, and then it says, delete the previous data that was not used anymore. We've already copied it over. Everybody's gotten off the train. Go destroy the train. OK? And then it says, all right, now we set our data variable to the larger array. OK, this variable didn't actually go away. It just said, now we've got new data that we're putting in that spot. And then the capacity is now the new capacity. That's all reserve does. It gives us our bigger train. OK. All right, and then size is the same. Valueat's the same. And average height is the same. OK. All right. Here is what this one looks like. Let's make it. And then let's run it. And what I've done, I showed you that list that has all the data in it. I've actually made it so that it's just a list of numbers. So what we can do is we can say, pipe in. This is a little thing that says, give me, I think I did this earlier, give me whatever file this is, send it to the heights dynamic tester by just as if it was typed in. And that makes it nice, because then you just have this whole thing, celebrity heights only, and we end up saying, OK, in my little list, there are 6,599 celebrities, and the average celebrity height, 68.1406 inches. OK, 68 inches. What is it, 5'8", did we decide? Yeah, but that's females and males, so whatever. Anyway, it's relatively tall, I mean, for the average, right? It's got some big people in there, too, like a bunch of basketball stars, I think, are in there, too. OK, All right, so that's how our new dynamic array actually works. OK, any questions on that before we go into more details about what this all means? Okay? You can look at that online if you want to look through the actual program. We'll probably do, the lab may have some dynamic arrays. If it doesn't, it'll have some dynamic something or others. Oh, by the way, labs start next week. Hopefully you'll have, hopefully we'll have the list out sometime next couple days about when you're scheduled for labs. Okay, and if it doesn't fit into your schedule and things change, just let us know. Okay, so that's our dynamic memory. What we've done is we've said, operating system, give me more memory. We've now said, here's the, now we're allowed to use as many members as we want. Okay, was there anything blatantly wrong about my program? I mean, it ran, right? It worked correctly. It looked at 99 different celebrities and gave me their average height. I happen to have a file called test data 100,000. So in like the year, whatever, 2300 or something, we have 100,000 celebrities in this little list, because of course the website will still be there 200 years from now. I've just made up numbers in that list, kind of a range. Okay? And if I do our heights tester and I pipe in this test data 10 or 100,000, watch what happens. Okay. So right now it looks like it's asking for a celebrity height, but I've actually piped this in. What it's doing is it's actually calculating all that, right? And you saw how long that took. You don't know exactly how long that took. We can figure that out. There's a Unix program called time. If you type time and then the same thing you just typed, test data 100,000, and you run it, okay, and you wait until the end, time actually gives us, there we go. It says it took 6.6 seconds to run this thing. The real time is the one you really care about. Okay, that's how long you actually sat there and waited for it. The other time is, look, it took 2.8 seconds for, actually I'm not, Bruce, do you know the difference between user and sys time? Bruce?
When your program runs, part of this is code you write.
Yes.
When you do things like get data from a file, the operating system is doing it.
Right.
And so some of your programs is the code that you wrote, some of the operating services that you're calling on. It breaks it down to how much time you spend running this class, how much time you spend reading from the file.
Got it. So there's a difference there. I'm not sure I buy these numbers necessarily for this program, but we'll get to that in a minute. Okay, so 100,000 celebrities. It takes a little while for your really fast 2014 computer to run, right? It takes a little bit of time to do that. How do we make that better? Okay, the big question is there a point in our program where we might be able to optimize this a little bit? Okay, yes?
Add more than one card at a time.
Yeah, add more than one card at a time. That's actually the exact place you're going to want to do that. Okay? Did anybody have any other ideas? There might be some others. I mean, we might have a better, maybe there's a better way to figure out the average, or maybe as we input the variables, we keep a running total of the average, okay, or something like that might speed it up a little bit too. But I like your idea of changing the actual number that we add in here. So let's see, celebrity heights dot. I'm going to forget to change this for the next class, and it's going to run great, and I'm not going to know why. Okay, so let's see. So if we go into, oops. No, not that one. Nano heights dynamic dots. There we go. Okay, so I'm going to go down here, and where did we do that? Where did we put in that request? Do you remember? Yeah, the reserve function. So if I go and search for reserve, it should. Nope. Hang on. Search for reserve, and there it is. Okay. So instead of, it's down here, the part that we care about. No, you know what? That isn't where we did it. The reserve is fine. It's the other two pieces that we care about when we actually do the reserving. So, hang on. Let's look at it again. Nope. All the way at the top. There it is. OK. All right, here we go. OK, so instead of 1, what should we pick? Let's pick 2. Why not? We'll make it 2. Instead of requesting 1 train car, OK, we're going to request 2. And that's going to give us a little buffer space for the next time. Okay, I suppose technically for the insert we should do the same thing, although it's not going to actually make a difference for our program. OK, so reduce to, OK, let's make it. Let's test it, time it again, and see how much better we did or if we did better at all. OK, so we went from 6.7 seconds to 4 seconds just by asking for 2 at a time. That's kind of cool. All right. Is there a better way to do it? Let's ask for more. What's another one we could ask for? 3. No, well, let's not just do 3. Yes.
100. If you double the size.
That's not a bad idea, actually. So we could just make up numbers that we might ask for, like 1, 2, 3, 4, whatever, right? But why don't we do exactly what you're saying? What's your name? Kate. Kate said, hey, double it each time. OK, that's not a bad idea. All right, so if we go here and we say instead of used plus 2, used times 2. So each time we do this, we're now going to say twice as much. Let's see how much better we do. OK, so make it again, and then run it. And oops, not run it. Hang on. Run it. There we go. Boom. All right, 0.046. OK, so this may be the best optimization you ever get out of a program, right? Going from, what was it, 6.7 seconds or something down to 0.04 seconds. Let's see, 0.6 would be 10, 0.06 would be, so you've got better than 100 times better performance by changing it so that you double the value. What are the downsides to doing that doubling? Yeah, I heard over here, using a lot of memory. Every time you do it, so really what this means is that if you start out with 2, and then you go to 4, and then you go to 8, then you go to 16, then 32, right? You get bigger, much, you get bigger exponentially, right? So you end up using a lot more space. And let's say just one more person gets on that train car, you've doubled the entire length of your train, right? Well, that might not be quite as efficient. There's lots of people who have done lots of thinking about the best ways to do these things, and doubling it is about what most programs end up doing. Some Java does it a little weird, a little different. They add like 1.9 times or whatever, and it's all based on what the programmers who have done a lot of tests on these think the average use case is going to be. Okay, but that's a good thing. And when you're trying to optimize your own programs, don't over-optimize. Like don't try. You don't need to really tweak these things. But the big things are what we're going to talk about. Okay. When we talk about analyzing programs, okay, you have to. We're going to get into some very specific details about how to analyze programs over this semester. And I just wanted to give you kind of a brief overview of the idea. But in your program, you're going to look for those things that are the bottlenecks. And by the way, what was really slowing us down in our program there? What was really doing the slowing down? Was it creating the memory? I don't think that was really it. Yeah.
You had to do a lot more copying.
Yeah. I mean, so let's say that our trains were actually filled with celebrities, right? And every time you added another celebrity you want to get on, you had to add one more seat. Not even a car. You have to add one more seat, and then everybody has to get off, right? And then you can add your next thing. If you do that every single time, that's what's taking up the time, is all that copying. Okay, all that copying is what's taking up all the time. And you end up, at that point, well, the celebrities will riot because every time they get to the, but you end up just spending too much time in the loop that you don't need to. You can optimize that away pretty easily. So in your own programs, look for places like that. We're going to look for these bottlenecks. Okay, we're going to look for these places where you spend lots and lots of time doing that. Okay. One last thing on this. On average, right, if you have 100 celebrities getting on these trains, right, how many copies do you have to make? How many individual copies do you actually have to make? Right? For each time you do that reserve, if you're going to do it. If this was n equals 100, right? If there are 100 celebrities, every time you do that, you have to add 100 different ones. Now, the next time you add 101, and the next time you add 102. We're not going to get into that level of detail, but it's on the order of, and that will mean something much more specific in the near future when we talk about it, the number of the celebrities, or the number of the values that you're doing with this array is going to be the important part that we're going to have to think about when we actually do some analysis of these programs. Okay? And that we'll get into, I guess next week we'll probably start a little bit of that. It's going to be, we're going to talk about big O analysis. And anybody heard of that before? Order N or big O analysis? Yeah, okay. A couple people have. It does not matter if you have not. We'll do all of that. Okay, I think that's enough for today. Any questions before we head out? All right, we'll see you Monday.